Too hot in here for you? Come on. Too hot in here? A little warm, yeah. Come here. Alrighty. Hello, everybody. We're back today. Oh, hope everybody's having a good day today. Friday. Oh, yeah. Woo! Weekend. It's the freaking weekend. Yeah, it feels good. It's going to be a good streaming weekend. We're getting a lot of subs like crazy. People loving the ML content, so we'll keep it rolling. Thanks so much for being here, everybody. Let's go ahead and without further ado, let's go get into today's stream. Reading on and continuing on with our learning in Deep Learning with Python, Chapter 2, right? Mathematical building blocks. We left off on the section Geometric Interpretation of Tensor Operations. So that's what we're going to pick up on today. Okay, let's start recording. Let's get into this. Alrighty. Geometric interpretation of tensor operations. Because of the contents of the tensors manipulated by tensor operations can be interpreted as coordinates of points in some geometric space, all tensor operations have a geometric interpretation. For instance, let's consider addition. We'll start with the following vector. We have capital A is equal to 0.5, 1. It's a point in a 2D space. It's common to picture a vector as an arrow linking the origin to the point as shown here. Let's consider a new point, capital B, which is 1, 0.25, which will add to the previous one. This is done geometrically by chaining together the vector arrows with the resulting location being the vector representing the sum of the previous two vectors. As you can see, adding a vector B to vector A represents the action of copying point A into a new location, whose distance and direction from the original point A is determined by the vector B. If you apply the same vector addition to a group of points in the plane and object, you would be creating a copy of the entire object in a new location. Tensor addition thus represents the actions of translating an object, moving the object without distorting it, in a certain direction. In general, elementary geometric operations such as translation, rotation, scaling, skewing, and so on can be expressed as tensor operations. Here are a few examples. Where we have translation, as you just saw, adding a vector to a point will move this point by a fixed amount in a fixed direction. Applied to a set of points, such as a 2D object, this is called a translation. Rotation. A counterclockwise rotation of a 2D vector by an angle theta, see figure 210, can be achieved via a product with a 2 by 2 matrix R equals to an array where we have the first row in the array is cosine theta, negative sine theta, and the second row in the array is sine theta, cosine theta. Scaling. A vertical and horizontal scaling of the image, see figure 211, can be achieved via a product with a 2 by 2 matrix S, where we have an array where the first row is horizontal factor, 0, and the second row is 0, vertical factor. Note that such a matrix is called a diagonal matrix because it has only non-zero coefficients in its diagonal, going from the top left to the bottom right. Linear transformation. A product with an arbitrary matrix implements a linear transformation. Note that scaling and rotation seen previously are by definition linear transformations. Affine transform. An affine transform, see figure 212, is the combination of a linear transform achieved via a matrix product and a translation achieved via a vector addition. As you have probably recognized, that's exactly the y equals to w at x plus b computation implemented by the dense layer. A dense layer without any activation function is an affine layer. Dense layer with ReLU activation. An important observation about the affine transforms is that if you apply many of them repeatedly, you still end up with an affine transform. So you could just have applied that one affine transform in the first place. Let's try with 2. Affine 2, parentheses, affine 1, parentheses, x, equals to w2 at w1 at x plus b1 plus b2 equals w2 at w1 at x plus w2 at b1. What does the at sign mean again? Map multiply, matrix multiply. Okay. It's really hot in here. Good. Okay. So you do W2 matrix multiply against the result of this plus this. You multiply matrices together, then you multiply the result of that against this. That's an affine transform, where the linear part is the matrix W2 at W1, and the translation part is the vector W2 at B1 plus B2. As a consequence, a multi-layer neural network made entirely of dense layers without activations would be equivalent to a single dense layer. This deep neural network would just be a linear model in disguise. This is why we need activation functions, like ReLU, seen in action in figure 213. Thanks to activation functions, a chain of dense layers can be made to implement very complex, non-linear geometric transformation, resulting in very rich hypothesis spaces for your deep neural networks. We cover this idea in more detail in the next chapter. A geometric interpretation of deep learning. You just learned that neural networks consist entirely of chains of tensor operations. Really quick, I didn't really understand that last section too well. Okay. The point of this paper like this is a tensor or matrix is basically a math machine that changes points. Here's the simple version of each one. Translation is moving something. If you add a vector to a point, you essentially get a new point. You move the point. 5, up, 1. Okay, got you. If you do this to every point in a shape, the whole shape slides somewhere else, like dragging a sticker across a table. Yeah, rotation, turning something. A rotation matrix is just a special math machine that turns points. If you rotate a square 90 degrees, every point changes position in a coordinated way. The matrix handles all the trigonometry for you. You can think of new point equals to rotation matrix map mole at the old point. Take this point and rotate it. The at means matrix multiplication. Scaling equals to stretching or shrinking. Scaling changes size. Example, multiply x values by 2 becomes wider. Multiply values by 0.5 becomes shorter. How a circle would become an oval. You can make it wider in the x direction and shorter in the y direction. Okay, by applying. And then linear transformation equals any combination of stretches, rotations, or skews. A general matrix can rotate, stretch, squash, or skew all at once, so matrices are like universal geometry transformers. The important deep learning connection. Now we get to neural networks. A dense layer does this. Y equals to capital W mat mole x plus b, where x is some input, W is a matrix, and b is some bias factor. That is it, literally. Transform the input, W, at x, and shift it plus b. That's an affine transform. So a dense layer is basically take points / data and geometrically reshape them. Why activation functions matter. This is the big idea. If you stack many dense layers, dense, 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 without activation functions, the math collapses into just one big matrix transform. Meaning, right, if we have matrix, map multiply, well, we map multiply this matrix, which maps multiply against this matrix, which map multiplies against this matrix, can always become W big at X. So multiple layers without activations are pointless. It's just one giant linear transformation pretending to be deep. ReLU changes everything. Python ReLU x equals to max 0 or x introduces non-linearity. Now the network can bend space, create curves, separate complicated patterns, learn complex relationships. Without activations, neural nets are basically fancy straight lines. With activations, they can model highly complex shapes and decisions. Intuition for what a neural network is doing. A neural network is repeatedly a geometrically transforming data, applying nonlinear bends, transforming data again, bending again, until all the data becomes easy to separate. Cat picture moves into the cat region, dog picture moves into the dog region, inside a huge mathematical space. That's why tensors and matrices matter so much in deep learning. They're literally the machinery used to reshape data geometrically. Okay, that makes sense. A geometric interpretation of deep learning. Hey John, how's it going? If you just learned that neural networks consist entirely of chains of tensor operations, and that all of these tensor operations are just simple geometric transformations of the input data, it follows that you can interpret a neural network as a very complex geometric transformation in a high-dimensional space, implemented via a series of single steps. In 3D, the following mental image may prove useful. Imagine two sheets of colored paper, one red and one blue. Put one on top of the other. Now crumple them together into a small ball. That crumpled ball is your input data, and each sheet of paper is a class of data in a classification problem. What a neural network is meant to do is figure out a transformation of the paper ball that would uncrumple it to make the two classes cleanly separable again. With deep learning, this would be implemented as a series of simple transformations of the 3D space, such as those you could apply on the paper ball with your fingers, one move at a time. Uncrumpling the paper balls is what machine learning is all about, finding neat representations. For complex, highly folded data, manifolds in high-dimensional spaces, a manifold is a continuous surface, like our crumpled sheet of paper. At this point, you have a pretty good intuition as to why deep learning excels at this. It takes the approach of incrementally decomposing a complicated geometric transformation into a long chain of elementary ones, which is pretty much the strategy a human would follow to uncrumple a paper ball. Each layer in a deep network applies a transformation that disentangles the data a little, and a data stack of layers makes tractable and extremely complicated disentanglement process. Okay, so we got to go back and take some notes for sure on all that stuff. That was a lot. Okay. So just like any computer we have that has the and, or nor, and so on operations, we have a couple of tensor operations that are useful to us. So we'll say tensor operations, right? Tensor operations are transformations learned by deep neural networks that can be reduced to a handful of tensor operations or tensor functions applied to tensors of numeric data. In our example, we're building a model of stacking dense layers on top of one another. This layer can be interpreted as a function, which takes input into a matrix and returns another matrix. A new representation of the data, especially the function allows where W is a matrix and B is a vector, both attributes of the layer. We have three tensor operations, a product mapmul going on, in addition. Right, so element-wise operations. We talked about these yesterday, right? These were where operations that are applied independently to each entry in the tensor are being considered. This means that operations are highly amendable. Okay, so then element-wise operations. Right, element-wise operations are let's get some feedback here. Element-wise operations do the same operation independently to every element. Perform the same operation independently to every element. No complicated geometry or matrix multiplication yet, just matching entries one by one. So for example, with vectors A and B, element operation would be addition. So you have like addition avoids right. And then an addition, you can also do it with just this simply with numpy rather than a loop. And you can then, remember, it timed it and said that the numpy was much more efficient. Okay, then we have broadcasting. So broadcasting, our earlier naive implementation of naive add only supports the addition of rank 2 tensors with identical shapes. But if the dense layer introduced earlier, we added a rank 2 tensor with a vector, what happens with the addition of the shapes of the two vectors being added differ. When possible, if there's no ambiguity, the smaller will broadcast and match the shape. Increasing, or like, it's kind of like casting, similar to typecasting, but for tensor shapes when performing addition of a 2D tensor plus a 1D tensor, the smaller tensor will be broadcast to match the shape of the larger tensor. So broadcasting consists of two steps. Axis, called broadcast axes, are added to the smaller tensor to match the NDIM, are added to the smaller tensor to match the NDIM of the larger tensor. 2. The smaller tensor is repeated alongside these new axes to match the full shape of the larger tensor. Let's look at a concrete example. Consider capital X with shape of 32 by 10 and Y with a shape of just 10. Right? We add empty axis to Y. So we expand the dims. We add empty axis to Y, whose shape becomes 110. Because it was just 10. Now we add an empty axis onto the 0. We expand the axis by, onto this, on the first axis. So now we have 110, right? One axis, 10 units inside that axis. Then we repeat Y 32 times. And so then we repeat this 32 times, those 32 rows, to match the 32 rows. Got you. In terms of implementation, no new rank 2 tensor is created because that would be terribly inefficient. The repetition operation is entirely virtual. When broadcasting, you can generally apply two tensors. Apply two tensor element-wise operations if one tensor has this shape and the other has this shape. Okay, then we talked about tensor products. don't go to school. I already graduated back in 2021. The tensor product, also called the dot product, right? Also called the dot product or matmul is so in NumPy, tensor product is done by using the npy.matmul function, and keros is keros ops matmul. Shorthand is the Python at operator. This image here. In mathematical notation, you write this. So the dot product would look something like this in Python for a naive implementation. We have noticed that the product between two vectors is a scalar, and the only vectors. So a scalar rank 0 tensors, a tensor that only contains numbers, is a scalar tensor, and that only you'll have noticed that the product between the two vectors is scalar, and the only vectors with the same number of elements are compatible for this operation. You can also take the product between the matrix y, x and y, which returns a vector. You can also take the product between matrix and vector y, which returns a vector where coefficients are the products between y and rows of x. Right, and then we talked about how this dot product diagram is pretty useful, where you say, okay, the values, the inner products, right, are equal to one another, and we can figure out this chapter is pretty dense. We're going to need like a pretty thorough breakdown for sure. So then we have this thing called tensor reshaping. A third type of tensor operation that's essential to understand is tensor reshaping. Although it wasn't using the dense layers in our first neural network example, we used it when we processed the digits data before feeding it to our model. Reshaping a tensor means rearranging its rows and columns to match a target shape. Naturally, the reshaped tensor has the same total number of coefficients as the initial tensor. Reshaping is best understood via examples. Take that. Transposition. So transposition, exchanging rows and columns. A matrix rows for its so transpose like such here. And then we read this part already. And if you add two tensors together, right? So then we had these types of geometric operations. So these are called geometric interpretations. Geometric interpretations of tensor operations. So translation right? Let me go back to my notes from before here where there were pretty good breakdown. Okay, so translation, adding a vector to a point. To a point will move this point by a fixed amount in a fixed direction. Applying a translation to a set of points, an object okay, so then you have this. We'll take this example here. Okay. 2. Rotation. So rotation, a counterclockwise rotation of a 2D vector by an angle theta can be via a product with a 2 by 2 matrix, this R equals to cosine theta negative sine theta sine theta cosine theta. Okay. And then we'll take this picture. Looks good. So you just apply a dot product of these values together to rotate a matrix to, move the points in a rotation manner, counterclockwise. Number 3, scaling. So in or out, like size, horizontal factor, vertical factor for scale. A horizontal factor imaging can be achieved via this. Okay, and then that looks good. Then we'll take this guy here. Nice. 4, linear transform. A product with an arbitrary matrix implements a linear transform. Note that scaling and rotation seen previously by definition are linear transforms. So it's just kind of like these, any sort of groups of these, I guess. Affine is affine transform. An affine transform is the combination of a linear transform via a matrix product and a translation via vector addition. The combination of a linear transform achieved via a matrix product and a translation achieved via a vector addition. So that's going to be this guy here. Map multiply against some other matrix X plus some vector addition. Right? So this is mat, it's W mat mul X plus B. This is the same computation that is implemented in the Keras layers dense layer. A dense layer without an activation function is an affine layer. Okay. Then we have 6, a dense layer with a ReLU ReLU activation. An important observation about affine transformations is that you could apply many of them repeatedly. Is that if you apply many of them repeatedly, so you map, multiply, and translate, map, multiply, translate, map, multiply, translate, you would still end up with an affine transform. Right? I guess, all of those stacked on top of one another is just an affine transform at the end of the day. It's not actually anything that changes our input significantly from its original parameters, right? Or is that what's kind of saying? So you could just have applied that one affine transform in the first place, right? If you sum up all of those affine transforms into one, right, it's the same thing as saying 10 multiplied by 2 is 20 is the same thing as saying 5 times 2 by times 2 is 20, right? If you're just wrapping the 10, you're just breaking it down into like a separate transformation, right? An affine transform. So let's try it with 2, right? So you affine 1 and then you have an affine transform on that value. Well, what does that mean? You have W1, right, at X plus B1. Well, that's being put into an affine 2, which is W2 map multiplied against that, plus B2 out here, right? Well, that just gives us this, map multiply against X, plus this. That's an affine transformation where the linear part is matrix W2 map multiply W1, and the translation part is this part, W at B1 plus B2. As a consequence, a multi-layer neural network made entirely of dense layers without activations would be equivalent to a single dense layer. This deep neural network would be a linear model in disguise. This is why we need activation functions like ReLU, seen in action in figure 12.13. Thanks to activation functions, a chain of dense layers can be made up to implement very complex nonlinear geometric transformations. right? This applies some sort of function in between the transformation, right? On top of the transformation, so that as we go layer to layer, we have separation. Let's ask about that. Trying to understand this section, how I see it is, okay, yeah, it makes sense that if you were to just kind of add all of these translations together and sum them and just do, you could do one, a fine transform it as one at once, right? If you were to just, okay, sum up all the transformations together, and then you could just do that transformation technically from the start to the end if you were just going to abstract out all the middle parts, like all the steps in between. But if we apply some RELU function on the layer before it's outputted, the input before it outputs to the next layer, we get, is this applying some sort of like separation in between each layer to where the transformations can actually have some sort of more grandiose effect on our inputs? I don't know. Am I thinking about this right in terms of like theory? Yes, you're thinking about it in the right direction. The key insight you're circling is the RELU breaks the ability to collapse everything into one single affine transformation. And that is exactly what gives your neural network their power. Let's build the intuition carefully. Without an RELU, everything just stays linear, right? You still go from point A to point B, right? And let's say you have like and maybe this is how I'm interpreting it. Let's go whiteboard here. Like, let's say you have like a linear line, for a simple example, right? Where here you have some point A, and here you have some point B. Well, and let's say these are affine transformations from point A to point B. So think about you have an image, right? You have some picture, and let's say it's a guy, right? And he's got his thumb up, right? Something like that. Well, let's say that you rotate the picture right here. You do an affine transformation and the picture rotates, right? Let's say that you do a transformation along here and the picture, let's say the picture kind of skews a little bit, right? Let's say you stretched them out, right? And let's say that here, but our end goal was to mirror the image, right? Our end goal was to mirror the image. Well, if it took all of this to figure out how to mirror the image, if the computer took all of these steps...
You're not that guy, pal. Trust me. You're not that...
If a computer had all of these layers implemented to do all these transformations, and we got to the end result of just a simple affine transformation of a reflection, well, why not just then reflect the starting point, right? That's kind of where I'm getting at this. I could be wrong, but if you kind of add all of these up, you still get to the end result of just a reflection. So you could kind of just abstract these away and just reflect from point A. Now, by applying some function at each phase, right, if we apply some RELU function at each phase, our outputs differ so much from these like affine transformations that we're able to, I don't know, like be creative. Like, let's keep going. Suppose you have this. Layer 1 equals this, and layer 2 equals this. If we substitute layer 1 into layer 2, just a simple substitution, and distribute, that's still just this. So mathematically, 2 layers is 1 layer, and everything is just one layer. There's no activation functions. The network never escapes linear algebra. It can only make lines, planes, and flat decision boundaries. No curves, no complex shapes. What the RELU stands for, RELU max 0 or x, this means that negative values must become 0 and positive values stay. That sounds simple, but geometrically it's massive. The crucial thing is RELU is not affine. You cannot write RELU of the affine transformation as this. That is impossible. So once RELU has been inserted between layers, you can no longer collapse the network into one matrix multiplication, right? You're doing kind of like some interjecting at each point, kind of like changing the state so it can't go back, right? Your idea about separation is close, some sort of separation in between each layer. That's actually a pretty good instinct. RELU creates regions in space where different rules apply. If x is less than 0, the output's 0, else it's x. So space gets partitioned. One behavior on one side, another behavior on the other. Now imagine millions of neurons doing this simultaneously. The network starts carving up into input space into many regions. Each layer reshapes space, cuts space apart, folds regions, selects regions, combines them. That's where the expressive power comes from. A geometric intuition. Imagine trying to separate red dots and blue dots. On paper, you only have linear transformations. You cannot rotate. You can rotate, stretch, shrink, or shift. But a tangled pattern stays tangled. You cannot untangle spirals from only affine transforms. Oh, like think about like three-dimensional shapes, like spirals that are intertwined, right? You can't rotate, translate, transform, or whatever, because and it'll still be intertwined. But REL introduces bending. After a RELU, some dimensions get zeroed out, others survive. This creates bends and folds in the geometry. A good mental image is affine transformations move and stretch the paper. RELU folds or clips parts of the paper. Now repeated layers can progressively untangle extremely complicated structures. This might sound a little abstract, but I recently watched the movie Interstellar, and they talked about black holes and how they look spherical because they're actually like a piece of like a plane in time that's bent to where you have like a hole pass through going from point A to point B. It's kind of bent. Think about a piece of paper with a hole on either side. That what that one scientist in the movie made that analogy of. Then you put the pencil through the folded piece of paper, so you're able to go across the paper in one instance. Does that have some sort of application here? Kind of crazy. Yeah, surprising that analogy is actually useful for building intuition about deep learning geometry. Not literally in physics sense, but conceptually very much yes. What you're describing from Interstellar is the idea that space can be bent so that points that are very far apart become close together through transformations of the geometry itself. This is extremely similar to what deep neural networks do to data. Uh-oh. We're building there in Interstellar! It's the end of the world! The important connection. Raw data often looks hopelessly tangled. Imagine pictures of cats, pictures of dogs. In pixel space, they're not neatly separated. It's to us, it's obviously a cat, but mathematically the points are mixed together in a gigantic, high-dimensional mess. A neural network's job is to essentially reshape the geometry of the data space until the categories become separable. Your paper folding analogy maps surprisingly well. Think about points drawn on a flat sheet, red points and blue points, and heavily intertwined. Linear transformations alone stretch, rotate, and skews, but cannot fundamentally untangle them. That's like sliding or rotating the paper without folding it. RALU is closer to folding space. Once non-linearities enter, regions can collapse, boundaries can form, dimensions can effectively turn off. Space can bend piecewise. Now points to that where difficult to separate can become easy to separate. So in a loose conceptual sense, deep learning repeatedly bends and reshapes the geometry of the representation space. Each layer creates a new coordinate system. Got you. Hey, Callison, how's it going? What's going on, user? Welcome in. How's it going, everybody? Hope everybody's doing good today. Okay, so we talked about a dense layer, right? So we'll say multiple affine transformations without RELU activation in between reduces down to just a single affine transformation, right? We need to add RELU activation at each layer, at each dense layer, in order to allow the data space to reshape and bend to separate the data away from a linear format. Something like that. A dense layer with a multiple affine transformation without activation functions collapse into a single transformation function. Adding RELU between layers introduces non-linearity, allowing the network to bend and reshape the representation of space so complex patterns can become more separable. Got you. That makes a lot more sense. Thanks to activation functions, a chain of dense layers can be made to implement very complex nonlinear geometric transformations. So we were able to, right, all of those negative values become stuck at positive, get stuck at 0, right? So it kind of reshapes the data field entirely. So now where we're kind of bound into these boundaries for finding resolutions, right? Something along those lines. It's kind of hard to really like conceptualize because you're thinking about numbers in like a 3-dimensional field, or in like a 2-dimensional field that are, no, I don't know. It's really strange. All right, this is about the ball analogy. Okay. Cool. I think we're good to move on here. I'm glad that we stopped and went back and looked at that because that made a lot more sense. Lagging here really bad. What's going on? Okay, we should be good. As you saw in the previous section, each neural layer from our first model example transforms its input data as follows. where we apply a map multiplication on the input and some other matrix and add a affine transformation, and then we do a ReLU operation on that. In this expression, big W and B are tensors that are attributes of the layer. They're called the weights or trainable parameters of the layer, the kernel and bias attributes respectively. These weights contain the information learned by the model from exposure to training data. Initially, these weight matrices are filled with small random values, a step called random initialization. Of course, there's no reason to expect that ReLU, mapmul input W plus B, when the kernel and bias are random, will yield any useful representations. The resulting representations are meaningless, but they're a starting point. What comes next is to gradually adjust these weights based on a feedback signal. This gradual adjustment, also called training, is basically the learning that machine learning is all about. This happens with what is called a training loop, which works as follows. Repeat these steps in a loop until the loss seems sufficiently low. Draw a batch of training samples X and corresponding targets Y equals true, Y underscore true. Run the model on X, a step called the forward pass, to obtain predictions Y underscore predictions. Compute the loss of the model on the batch, a measure of the mismatch between the predictions and the true from the output Y. Update all weights of the model in a way that slightly reduces the loss on this batch. You'll eventually end up with a model that has a very low loss on its training data, a low mismatch between predictions, Y pred, and expectation targets, Y true. The model has, quote, learned to map its inputs to correct targets. From afar, it may look like magic, but when you reduce it to elementary steps, it turns out to be simple. Step 1 sounds easy enough. It's just input-output code. Step 2 and 3 are merely the application of a handful of tensor operations, so you can implement these steps purely from what you've learned in the previous section. The difficult part is step 4, updating the model's weights, given an individual weight coefficient in the model. How could you compute whether the coefficient should be increased or decreased, and by how much? One naive solution would be to freeze all weights in the model except the one scalar coefficient being considered and try different values for this coefficient. Let's say the initial value of the coefficient is 0.3. After the forward pass on a batch of data, the loss of the model on the batch is 0.5. If you change the coefficient's value to 0.35 and rerun the forward pass, the loss increases to 0.6. But if you lower the coefficient to 0.25, the loss falls to 0.4. In this case, it seems that updating the coefficient by negative 0.05 would contribute to minimizing the loss. This would have to be repeated for all coefficients in the model. But such an approach would be horribly inefficient, right? We're having to individually adjust one coefficient and then adjust it for each of them, and it'd be a huge O of n squared kind of problem here, I think, right? But you probably would have to go even back, not even, and readjust even further after even doing an O of n squared pass, I believe, right? It's not like you can just be done. You probably can, once you alter the last weight, you probably have to go back to the first one again and keep going. It's probably like an infinite passing. But such an approach would be horribly inefficient because you need to compute 2 forward passes, which are expensive, for every individual coefficient, of which there are many, usually at least a few thousand, and potentially up to billions. Thankfully, there's a much better approach: gradient descent. Gradient descent is the optimization technique that powers modern neural networks. Here's the gist of it. All the functions used in our model, such as map, mul, or addition, transform their input in a smooth and continuous way. If you look at z equals to x plus y for the instance, A small change in y only results in a small change in z. And if you know the direction of the change in y, you can infer the direction of the change in z. Mathematically, you'd say these functions are differentiable. If you chain together such functions, the bigger function you obtain is still differentiable. In particular, this applies to the function that maps the model's coefficients to the loss of the model on a batch of data. A small change of the model's coefficients results in a small predictable change of the loss value. This enables you to use a mathematical operator called the gradient to describe how the loss varies as you move the model's coefficients in different directions. If you compute this gradient, you can use it to move the coefficients all at once in a single update rather than one at a time, in a direction that decreases the loss. If you already know what differentiable means and what gradient is, you can skip the next two sections. Otherwise, the following will help you understand these concepts. All right, so it looks like we're going to get into some calculus here. Right? If you haven't had any calculus exposure yet, here we go. What's a derivative? Consider a continuous smooth function. F of x is equal to y. Mapping a number to x to a new number, y, we can use a function, Consider a continuous smooth function, f of x is equal to y. Mapping a number x to a new number y. Right, you put into the function some number x, and it gives you out some output y. And this function makes up this line here, right? We can use the function in figure 2.15 as an example. Sorry. Because the function is continuous, a small change in x can only result in a small change in y. That's the intuition behind continuity. Let's say that you increase x by a small factor, epsilon x. This results in a small epsilon y change to y, as shown in figure 2.16, right? If we slightly change x, we get a slightly, change to y. So if we move up from our x here to here, our y goes from here to here, right? We get different y values. In addition, because the function is smooth, its curve doesn't have any abrupt angles. When epsilon x is small enough around a certain point P, it's possible to approximate f as a linear function of a slope a, so that epsilon y becomes a times epsilon x. In addition, because the function is smooth, its curve doesn't have any abrupt angles. When the change in x is small enough around some certain point P, right, it's possible to approximate f as a linear function of slope a, so that epsilon y equals f of x. F of that equals to y plus a times epsilon x. Okay, so what it's doing here is this is just being substituted in for epsilon y, right? Right? You're applying some epsilon x onto x such that it's so small to a certain point P that you can approximate f as a linear function of slope a, right? So that just fills in for epsilon y here. Right? If you move epsilon x, causing epsilon y to change, causing y to change with corresponding epsilon y adjustment, we can substitute a in for that and compute potentially a slope approximation. Obviously, this linear approximation is valid only when x is close enough to p. That's what I was thinking, right? So I was like, well, think about it. If you're just calculating some individual point, right, that doesn't necessarily tell you the slope of the line all the way down here at this point. Because if you draw a line, that's just a linear line, and this actually looks like some, elephant curve, whatever, some parabolic curve, or a parabolic curve. So that would make sense, right? Is that whenever the x point has to be close to this p, you can infer the slope of that point, right? Think about it like this. That makes a lot of sense. Think about it like this on a more simple term. Let's say we have a curve like this. Let's say we have a bigger curve like this, right? Well, if we say our point x is down here, and we say our point y is over here, right? Well, trying to compute like a slope between these 2 points, that doesn't very well represent our curve, right? Because, in theory, if we were to say that this is like an xy plane, and this is like x, that this point here is like at 1, 1, 0, and this point is at like 5, 5, or something like that, right? That's pretty far apart, right? But let's say that we have a point actually, let's say instead of having our starting point be there, let's say our starting point was here, right, x. And then we have some value, some epsilon x, some distance away from x, right, that's small enough, point P, right, we can compute a slope. This region, if we zoom in, right, if you take a curve and zoom in really close, it looks like a straight line, right? Because you don't have the perspective of the curve, right? So you technically, if you have some point, epsilon x, some distance from x, some new point P, right, this distance is epsilon x, right? This can be approximated as like a linear slope because it's close, it's kind of like zoomed in on that curve, right? That makes sense. Let's go ahead and let's recap that. So now we're moving into derivatives, right? Differentiable functions, and we're reviewing like what is derivative here, right? So we know if we have some point xy, or some values xy, if we make some sort of incremental adjustment to the x, we have some sort of corresponding incremental adjustment y, as long as our function, right, is continuous, right? It falls along that line, we will adjust our y, some epsilon y, not proportional, but in some sort of relation to the epsilon x distance, however that falls, whatever ratio for that function is. Now, the thing is that with derivatives, right, what it's saying is that if we have some epsilon, some movement from the point that is so small that we could approximate a local linear approximation of slope between x and that new point P, which the difference of it is that epsilon x. And so although the grand picture of our function may not match the individual slope of this kind of more smaller localized section, right? Think about like a big circle. If you zoom in on one small section of a circle, it kind of looks like a linear line. You don't really see the perspective of the curve. That's why you have these people out there that think the earth is flat, right? Because they don't see the perspective of the curve, they're not zoomed out, right? It's the same type of thing. Yes, that's the fundamental right intuition for derivatives and differentiability. Describing one of the core ideas in calculus, smooth functions become approximately linear when you view locally enough. That is what exactly the conceptual foundation behind derivatives, tangent lines, and eventually gradient descent is in deep learning. You're zooming into a circle until it looks flat, as an analogy is excellent. Suppose you have a function y equals f of x. At some point x, you slightly change that input, x plus some change, delta. You observe some corresponding change to the output, right? Right? F of x, well, you add x to e, right? That gives you a resulting f of x plus e, which is equal to y, right? The derivative measures how sensitive the output is to tiny changes in the input. That's the key concept, right? So if we just slightly move that point P, like if we create a point P, okay, cool. That's what I was missing. So the derivative is the observation or sensitivity to those tiny changes. So if our curve or if our function has a lot of kind of drastic variability, sharp turns for some point x, and we cause some minor delta away from that point, and it causes some drastic resulting change in our y value, what does this tell us? Now you're getting into the really important intuition behind derivatives and gradients. If a tiny change in x causes a huge change in y, then the derivative magnitude is large. That tells us that the function is highly sensitive at that location. Geometrically, the curve is too steep there. The local slope has large magnitude. Suppose that f of x is equal to x squared, so some, x squared function. Near 0, tiny changes in x barely affect y. The slope is small. But near x100, where we're at that kind of asymptotic behavior, a tiny change in x causes dramatic changes in y. We go way higher by moving x slightly, increase or decrease, or we move x way lower if we're near that asymptote behavior. So in this example, as we caught, in certain regions of our x squared function near the origin, we have a somewhat kind of linear approach, and we can see that by taking the derivative along those various points up to some value. Now, once we reach some threshold, we notice some ramping going on, which is behavior of the exponential function, and as a result, right, any small change in x causes drastic changes in y. If we increase x near the asymptote, our y value goes way higher, vice versa, for lowering. Sorry, it's quadratic, my bad. Exponential is the other way, the e at the front. Sorry, my bad. Sorry, quadratic function. I misspoke. This function is smooth everywhere, no asymptotes. Right. It has no asymptotes? Oh, I'm dumb. Hold up. That's right. Let me open up Desmos. I haven't looked at one of these in a while. Oh yeah, not asymptotes, but just the ramp of like the parabola. Increasingly steep as the absolute value of x gets larger, no matter what direction, right? So near x we have zero slope. right? We start drastic. The farther you move away from origin, the more sensitive y becomes to change in x. That part is, your intuition is correct. That was my bad. I didn't mean that. Okay. Cool. That makes sense. The slope a is called the derivative of f in p. If a is negative, it means a small increase in x will cause p. If a is negative, it means a small increase in x around p will result in a decrease of f of x, as shown in figure 217. And if a is positive, a small increase in x will result in an increase of f of x. Further, the absolute value of a, the magnitude of the derivative, tells you how quickly this increase or decrease will happen. That makes sense, right? A is the slope of this derivative. A negative slope would show a decrease in the f of x value, resulting value, whereas a positive one would show you a resulting positive value, right? The magnitude, the absolute value of the slope, right? How the magnitude of its steepness tells you how quickly this will increase or decrease, right? The steeper the line, the higher the ramp factor is for this. That makes sense. For every differentiable function, f of x, differential means can be derived. For example, smooth, continuous functions can be derived. There exists a derivative function, f prime of x, that maps values of x to the slope of the local linear approximation of f in those points. For instance, the derivative of cosine of x is negative sine of x. The derivative of f of x equals to a times x is f prime of x equals to a, and so on. For every function f of x, differentiable means can be derived. For example, smooth continuous functions can be derived. There exists a derivative function, f prime of x, that maps values to x, that maps values of x to the slope of the local linear approximation of f in those points. I'm not really following this. Suppose you have f of x. The derivative, f prime of x, is itself another function. That new function tells you what is the slope of the original function at every possible x. Example, a linear function. Suppose f of x equals to 3x. This is just a straight line. The slope is always 3. So f prime of x is equal to 3, meaning no matter where you stand on the line, the local slope is always 3. Quadratic, f of x equals to x squared. The derivative is f prime of x equals to 2x. Now the slope depends on location. At x equals to 1, the slope is 2. So this tells you the slope at x, basically. So the derivative function describes how steep the curve is at every point. Your local linear approximation idea. This sentence, slope of the local linear approximation, is extremely important. It means, at any tiny region around a point, the function behaves approximately like line about a tangent. The derivative gives the slope of the tangent line. Cosine example. The book says d over dx cosine x equals to negative sine x. So the derivative of cosine x is equal to negative sine x. Meaning, the slope of cosine x at every point is described by a negative sign. So if we go to Desmos, and we do cosine x and then negative sine x, example, at x equals 0, cosine of 0 is 1. The negative sine of 0 is 0. So cosine is flat there. So x equals 0. Yeah, that makes sense, right? It's 0 and 1, and it's the peak, so it's a flat slope there. So negative sine of 0. Oh, is 0, so it's 0, the resulting y value is 0. So cosine is flat there. Okay, got you. So what's happening here? In red, we have the cosine function. And in blue, we have the negative sine function, which is the derivative of cosine x. Right? Well, we want to know what is this. And this function here is just telling us the slope at any given point x for this function. Right? This function gives us out answers, whatever. But this function tells us the slope at any point x for this function. What does that mean? Well, if we're looking at x equals 0 for the cosine of x equals 0 for the cosine of x gives us a value of 1. Okay, cool. For the cosine of x, the value of x equals 0 is 1. Well, what is the slope approximation at cosine x equals 0? We can figure that out by taking the derivative of cosine x and plugging in that value for that function. So derivative of cosine x is equal to negative sine x. We plug in 0, which is we're trying to solve for the slope at 0 for cosine x, which is 0 sine x, negative sine x 0, which is 0. The output is 0. The y value is 0. What does that tell us? The slope for negative cosine x is 0 at 0, right? So, which makes sense because here it is, and the slope is 0. It's a flat line, right? If I do y equals to 1 here, right, that line is our slope, right? It's 0. That makes sense, right? So the derivative got you. So in the example of cosine x, where x equals 0, our y value that's spit out in that function is 1, right? We don't really care about that if we're trying to find, okay, what's the derivative at x equals 0 of cosine x? Well, we know that the derivative function of cosine x is negative sine x. So we put in 0 for x, just like we would, and it gives us out a corresponding y value. Now this value isn't the answer of cosine x, right? Because this is 0 plugged into negative sine x. But we know that negative sine x is the derivative of cosine x, and we know that derivatives represent the slope at any given point for a function. So for any given point x, the slope or the local slope of that point for cosine x is equal to the negative sine of x. So which, when you take 0 into negative sine of x, it gives you a y value of 0, which corresponds to the flat slope at the peak of that rising cosine wave. Yes, that's exactly correct. Now you separated two important ideas. The value of the function and the slope of the function. Those are different quantities. For f of x cosine x, at x equals 0, cosine is 1. That's the height of the curve at that point. But the derivative asks, how is the function changing at that point? The derivative of the function is this, right? Now, that's the thing is there's calculus process that you learn about, a lot of like substitution methods, different types of methods in order to solve these derivatives for various functions, right? But we just know we know this one off the top of our head. We're not trying to solve derivatives in this we're not doing calculus, right? But if you're questioning, well, how did they get negative sine x? If you've never taken calculus, well, you have a lot of these kind of methods you learn, like exponential methods, and all these different substitutions and whatnot, or what different things stand for. It's honestly like kind of pretty similar to like physics equation substitutions. If you've ever taken college level physics, like the first 2 semesters of physics, that's pretty much all you're doing is just substituting equations in for variables and stuff, and kind of doing just nested substitution of functions to solve these physics equations, and then kind of learning some theory behind it. Got you. That makes a lot of sense. Being able to derive functions is a powerful tool when it comes to optimization. The task of finding values of x that minimize the value of f of x. If you're trying to update x by a factor of epsilon x to maximize f of x, and you know the derivative of the function f, then your job is done. The derivative completely describes how f of x evolves as you change x. If you want to reduce the value of f of x, you just need to move x a little in the opposite direction from the derivative. Right? So how does this play into what we're learning about here? Well, we know that deriving functions if we're trying to update x by a factor of epsilon x to minimize our loss function, right? And you know the derivative of f, right? We know a function that'll give us the slope, right? We would want to find a slope, so let's ask this question. I know we're kind of moving slow here, but this is where we're really learning here. So in this paragraph then, when we apply this derivative calculus concept to our machine learning and deep learning, as we're trying to adjust or update some value x, right, which would be our coefficients, or maybe our bias values or whatever, right, by some factor epsilon x, which will hopefully in our goal is to minimize the loss function f of x. If we know the derivative of the function that we're trying to solve for, right, then we can predict without actually having to do plug and chug work. Okay, if we go ahead and insert some x value, we know the slope is positive or negative at this point in time. So we can kind of just either go for it if it's negative to reduce our function, or do the opposite if it's positive, because we obviously want to reduce the function. Does that make sense? Yes, that absolutely makes sense, and you're very close to the core idea of gradient descent. You're correctly connecting derivatives, slope, parameter updates, and minimizing loss. Let's tighten the intuition a little. The setup. In machine learning, loss equals to the function of parameters. The parameters are weights and biases. The loss function tells us how wrong is the model right now. What derivative tells us? The derivative tells us if I slightly change this parameter, what happens to the loss? So, a positive derivative, if we increase x, the loss increases. Moving right is bad. Moving left is good. We want to reduce the loss, right? In terms of increasing x, decreasing x. Moving right on an axis, left on an axis. You really have to think and visualize this as axes and like a geometric plane in your head. It really helps. If the negative derivative, right, meaning that we have a negative slope for this point at this function, right, we know that this loss decreases, and we can go ahead and increase this parameter value, increase this bias. That's the key optimization. For reducing the function, you don't need to randomly guess parameter values. The slope tells you which direction is downhill. One small correction. We can predict without actually having to do the plug and chug work, kind of, but important. We are still having to evaluate the function derivatives numerically. We're just using local slope information instead of brute force searching. So my question is more of like a theoretical or conceptual. How does this apply to every x value in the function, right? If you're individually looking at, these biases, which are these x values that you're tweaking, biases and weights that are being applied into the function, right? At some given individual x instance in the geometric plane, right? If we're just evaluating the scope, the local scope of some kind of buffered range, for some, epsilon x from x, are we having to compute this across? Can you help me tie this together? Yes, this is exactly the conceptual hurdle people hit when moving from a single variable calculus into neural networks. You're asking, how does this local step idea or local slope idea scale into millions of parameters all interacting together? That's the right question. The key realization is, in neural networks, the x is no longer a single number on a 2D graph. Instead, x is the entire parameter vector, meaning all weights and biases together. In basic calculus, you imagine y equals f of x, with one input and one output. That's exactly what I was visualizing. So the graph is a curve. The derivative, f prime of x, tells us the slope along that one dimension. In neural networks, now imagine loss equals to a function with all of these individual weights in them, up to some weight n. Every weight, every bias simultaneously is dependent on the loss. The loss depends on these. So instead of a 2D curve, you know how a giant three-dimensional surface, that would make sense, right? You have multiple dimensions, not just a single x value being fed into the function. Right? You have an entire vector being fed into the function. That would make sense, right? We have a bunch of weights and biases. Now, is the individual weight and bias for each layer going into the function? Like, is it weight for layer 1, or is these weights 1 through weight n all at one individual layer? If that makes sense. Now, you would compute a derivative function on f of all of these weights dependencies, right? And that would give you a summarized, or vectorized look or scope for that individual vector node, which has many dimensions. Crazy stuff. We're really getting into it here. You're extremely close now. The main thing is to organize the hierarchy correctly. The weights are not one weight per layer. Instead, each layer contains many weights and biases, and the loss function depends on all of them simultaneously. Think about one dense layer. Suppose input size is equal to 3, and we have neurons is equal to 4. then the layer has a weight matrix and a bias vector. So the shape is 4, 3, 4 neurons and 3 weights per neuron. Right, 4 rows, 4 neurons, 3 columns, 3 attributes per neuron. And bias is, the shape of the bias is just 4, 1 bias per neuron. So the single layer already has 12 weights plus 4 biases equals 16 parameters. Now you have multiple layers on their own, so the network has millions of parameters. The loss depends upon all parameters. This is a function over a gigantic parameter space. Now the derivative idea generalizes, you asked. How to compute a derivative function on all, do we compute a derivative function on all these weights dependencies? Yes. But now we use partial derivatives and gradients instead of a single ordinary derivative. A gradient equals a vector of sensitivities. For every parameter, what the heck? Okay. Okay, derivative of tensor operation, the gradient. The function we were just looking at turned a scalar value x into another scalar value y. You could plot it as a curve in a 2D plane. Oh, it looks like we're about to get into it right here. Now imagine a function that turns a tuple of scalars, x, y, into a scalar value z. That would be a vector operation. You could plot it as a 2D surface in a 3D space, indexed by coordinates x, y, and z. Likewise, you can imagine functions that take as input matrices functions that take as input rank 3 tensors, etc. The concept of derivation can be applied to any such function, as long as these surfaces they describe are continuous and smooth. The derivative of a tensor operation, or tensor function, is called a gradient. Gradients are just the generalization of the concept of derivatives to functions that takes tensors as inputs. Remember how, for a scalar function, the derivative represents the local slope of the curve of that function. In just the same way, the gradient of a tensor function represents the curvature of the multi-dimensional surface described by the function. It characterizes how the output of the function varies when its input parameters vary. Let's look at an engine grounded in machine learning. Let's look at an example grounded in machine learning. Consider an input vector x, which is a sample in the data set, a matrix W, the weights of a model, a target, y equals true, what the model should learn to associate to x, and a loss function, loss, meant to measure the gap between the model's current predictions and y true. We can use W, the weights of a model, a matrix, to compute a target candidate, y prediction, and then compute the loss or mismatch between the target candidate, y prediction, and the target, y true. We use the model's weights, W, to make a prediction for x. We map multiply x and the weights to get predictions, y. We must estimate how far off those predictions are by loss function, y predictions, and y true. Now, we like to use gradients to figure out how to update big W, our weight models, to make loss values similar. How do we do that? Given fixed inputs x and y underscore true, the previous operations can be interpreted as a function mapping values of big W. the model's weights to loss values. Given fixed inputs x and the true values of y, the previous operation can be interpreted as function mapping values of y to the loss values. Loss value equals f of big W. F describes the curvature or high-dimensional surface formed by loss values. Okay, so if loss value, you're saying that f of big W equals to this, basically. Let's say the current value of big W is W0. Then the derivative of f in the point W0 is a tensor grad loss value W0 with the same shape as big W, where each coefficient, gradient loss value, comma big W, index I, index J, indicates the direction and magnitude of the change in loss value. You observe when modifying weight row 0 what is going on here? It's losing me, boys. This chapter is brutal. Ugh. I'm burning out here. First, I've already been going an hour and 42 minutes and we haven't even really gotten that far, it feels like. This is a slow burn, yo. Stochastic gradient descent. This is tough. What does this mean? The light's really going. Come on. This is one of the most important passages in early deep learning because it connects calculus, tensors, gradients, optimization, and learning itself. And honestly, based on your earlier questions, you're already 80 to 90% of the way there conceptually. Let's tie it together carefully. The model is a function. You have y predictions is equal to x map multiplied w. This means that input x transformed by some weights w produces predictions y predictions. Then loss value is calculated by computing loss input of y predictions and y true. How wrong was the prediction is the loss value. The critical shift in perspective. At inference time, x points to prediction. But during the training, we temporarily treat x, y true as fixed constants. Now the thing changing is big W. So the loss becomes loss equals to function of big W. We were originally doing y prediction is this. We insert that into here. Y true and x are constant, so we just get loss of big W. How does the loss change as the weights change? This creates a high dimensional surface. If you had one weight, loss is equal to F of W. You could draw a 2D curve. But with thousands/millions of weights, loss equals to F of big W. You now have a hyper surface in an enormous dimensional space. Each point corresponds to one complete network configuration. What the gradient actually is. Suppose W dot shape equals to 3, 3. So we have a 3 by 3 weights. Then gradient loss on those weights also has the shape of 3, 3. Why? Because every weight gets its own derivative. Each entry answers, if I slightly change this weight, how does loss change? Suppose this, meaning increasing that weight increases loss strongly. So we compute a gradient I don't know what this means. I'm out of messages, shoot. What, any, this. W is a matrix of weights. Example, right? All these different weights. So, weight index 1, 2 means the weight in row 1, column 2. Okay, it's just doing a different way of indexing. Now the loss depends on all weights. You change one weight, the loss changes a bit. So what is grad loss W index 1, comma 2? Formally this, I think a tiny experiment turns you take the current model, you slightly increase the weight of this individual weight by a tiny amount, and you recompute the loss and you compare. Now interpret the sign and magnitude. So we compute the gradient and we get an increase of 5. So you increase the weight a little, increases the loss increases by a lot. Okay. The function we're just looking at turned a scalar value x into another scalar value y. If you plot it as a curve in a 2D plane, now imagine a function that turns a tuple of scalars. Okay, we already did that. So the concept of derivation can be applied to any such function as long as the surfaces they describe are continuous and smooth. The derivation of a tensor operation or tensor function is called a gradient. Gradients are just the generalization of the concept of derivatives to functions that take tensors as inputs. Remember how for a scalar function the derivative represents the local slope of the curve of the function. In just the same way, the gradient of a tensor function represents the curvature of the multidimensional surface described by the function. It characterizes how the output of the function varies when an input's parameter varies. Let's say an example grounded in machine learning. Consider we have some input vector x. We have a matrix W, which is our weights, and we have targets y, and a loss function. So we can make some predictions by applying our input to our weights, right? This is a new representation or a prediction for an output prediction, right? It might not be close to what our desire. We need to compute it to a loss value. We compute a loss value here, right? Now we'd like to use gradients to figure out how to update our weights to make the loss value smaller. How would we do that? Given fixed inputs of our vector and our true expectations, the previous operation can be interpreted as a function mapping values of just weights. The model's weights to loss values. Let's say the current weight is W0. Let's see the current value of W is W0. Then the derivative of F in the point W0 is a tensor of gradient loss value W0. Right, this is the current value of the weights. With the same shape as W, where the coefficient indicates the direction magnitude of change in loss value to zero when modifying that individual weight. Got you. That makes sense. So you're modifying this individual weight at this index, right? And the gradient, remember, is this the derivative at this value. So this right here indicates the direction of the change in the loss value you observe when modifying this individual weight. So we're modifying this individual weight, and this is that observation that we noticed when we modified it, the gradient or the derivative. The tensor grad loss value W0 is the gradient of the function f of big W equals the loss value in W0 for some weight, also called gradient of loss value with respect to W around W0, right? Remember, the gradient is just another word for the, derivative applied to this vectorization as a whole, right? It's like the concept abstracted to that. Let's say the current value of W is W0. Then the derivative of F in the point W0 is a tensor, right? Gradient loss value comma W0 with the same shape as W, where each coefficient at some weight indicates the direction and magnitude of the change in loss value. You observe when modifying some weight that tensor grad loss value for that weight is gradient the function. That tensor grad loss value comma weight 0 is the gradient of the function f of big W equals the loss value in weight 0, also called, quote, gradient of the loss value with respect to W around W0. Right, the derivative of the loss value with respect to W around some specific weight W0. The tensor operation, gradient f of big W comma W, which takes an input, a matrix W, can be expressed as a combination of scalar functions grad underscore I j of f of big W comma W underscore I of j. Each would return the derivative of loss value equals to f of big W with respect to the coefficient for some weight I and j of W, assuming all other coefficients are constant. gradient underscore ij is called the partial derivative of the function f with respect to some specific weight I and j. So the gradient is just an abstraction on the 2D formation or formality of derivatives, right? But being applied now to a vector object, right? So we have some weights, right? W, right? This is a matrix of weight values, right? With some shape. It could be 2D, 3D, or whatever. We compute a gradient given some loss value for some specific weights, right? This would indicate this specific like gradient loss value comma big W0 at some index I and j, right? This computation is the same representation as f prime of x, right? Where it's just the magnitude and direction of change in loss value when observing and modifying some specific weight at I, j, or dimensionality indexing. So the whole point of a gradient is just right, a loss value gradient is just a the gradient is just a derivative of a vector at a certain point in the overall function with respect to that specific point of weights. You're very close, but there are a couple of important precision fixes. A gradient is an extension of derivatives to many variables. Yes. Weights from a vector or tensor matrix. Yes. The loss is a function of all weights. The loss is a function of all of the weights. We compute how loss changes when we tweak each weight. So far, correct. The gradient is a collection of derivatives of a scalar function with respect to each component of a vector / tensor output. So, input is some tensor / vector W. Output is some scalar value, which is loss. What the gradient actually is. If the loss equals the function of all of the weights, the gradient of some function of some weight, of that function at some weight, is a list of all of the, what is this sign here? So the gradient is a tensor of partial derivatives, not a single derivative. You said same as f prime of x. Yes, conceptual, with one important distinction. In one-dimensional calculus, f prime of x is the slope of a curve. In multivariable calculus, it's the slope in many directions. F prime of x is the slope of one curve. Whatever this is, f of w, the gradient f of w is the direction of the steepest increase in a high-dimensional space. What direction and magnitude really mean? The most important model shift. It is a vector pointing in the direction of the steepest increase of the loss. So direction equals to how change of all weights together. Magnitude is how sensitive the loss is overall. Concretely, what does grad, loss value, comma, weight 0 represent? You saw earlier that the derivative of function f of x of a single coefficient can be interpreted as the slope of the curve of f. Likewise, grad loss value, comma, w0 can be interpreted as the tensor describing the curvature of loss value equals to f of big W around weight 0. Each partial derivative describes the curvature of f in a specific direction. We just saw how for a function f of x you can reduce the value of f of x by moving x a little in the opposite direction from the derivative. In much the same way with the function f of big W of a tensor, you can reduce loss value equals to f of big W by moving W, the weights, in the opposite direction from the gradient, such as an update of W1 equals to W0 minus step times the gradient of f of W0, where step is a small scaling factor. That means going against the curvature, which intuitively should put you lower on the curve. Note that the scaling factor step is needed because grad, the gradient loss value of that W0, only approximates the curvature when you're close to W0, so you don't want to get too far away from W0. Interesting. Let's go ahead and see if I can find like a video to maybe visually explain this a little bit better. Deep learning gradient descent. Hold on. Let me put in my headphones here. Where'd my headphones go? Let me grab my headphones. I think they're in the other room or something. Where'd they go? Alright. Let's watch this video.
Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have two main goals for this video. The first is to introduce the idea of gradient descent, which underlies not only how neural networks learn, but how a lot of other machine learning works as well. Then after that, we're going to dig in a little more to how this particular network performs, and what those hidden layers of neurons end up actually looking for. As a reminder, our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of 784 neurons in the input layer of the network. And then the activation for each neuron in the following layers is based on a weighted sum of all the activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of two hidden layers here with 16 neurons each, the network has about 13,000 weights and biases that we can adjust. And it's these values that determine what exactly the network actually does. Then what we mean when we say that this network our goal here is the classic example of handwritten digit recognition, the hello world of neural networks. These digits are rendered on a 28 by 28 pixel grid, each pixel with some grayscale value between 0 and 1. Those are what determine the activations of...
Okay, so each pixel, right, 28 by 28, with 784 pixels is a
784 neurons in
the input layer of the network. So the input layer of the network, right, is the data points corresponding to the actual values on the image, right?
The input layer of the...
So we feed into the network the 784 pixel data numbers, so these would be vectors of data, but this would be a two-dimensional matrix, so it would be a 2D tensor.
You're not that guy.
Okay.
Okay?
You?
Absolutely.
A 2D tensor.
You're
And
not that guy, pal. Trust me. You're not that
we've
guy.
been really popping off on the subs lately, so I might
Absolutely.
have to turn that off. Hold up real quick. I want to go to... what's it called? Streamlabs. Let me see here. Okay. Should be good. Okay.
of the network. And then the activation for each neuron in the...
Okay, so the activation of each neuron in the following layer is based on a weighted...
following layers is based on a weighted sum of all the activations in the previous layer plus some special number.
Okay, so you compute...
based on a weighted sum of all
of the the weighted sum. So you feed in all of the input data, all of the raw data pertaining to that image, audio file, text file, whatever. You then, in each following layer of the network, you apply weights to the activation of these values.
The activations in the previous layer plus some special number called a bias. Then you compose that sum with some other function, like the sigmoid squishification or a ReLU, the way that I walked through last video. In total, given the somewhat arbitrary choice of...
ReLU, that was a sigmoid function, and so you're just applying either some sort of function in between the layers.
Two
right?
hidden layers here with 16 neurons each. The net...
So we have 784 inputs, 2 hidden layers of 16 neurons each, of 16 bias each, plus 10 for the...
The network has about 13,000 weights and biases that we can adjust.
784 inputs times 16 weights in the first layer at each 16 nodes, plus 16 weights for each 16 nodes in the next layer, times 10.
And it's these values that determine what exactly the network, actually does. Then what we mean when we say that this network classifies a given digit is that the brightest of those 10 neurons in the final layer corresponds to that digit. And remember, the motivation that we had in mind here for the layered structure was that maybe the second layer could pick up on the edges, and the third layer might pick up on patterns like loops and lines, and the last one could just piece together those patterns to recognize digits. So here, we learn how the network learns. What we want is an algorithm where you can show this network a whole bunch of training data, which comes in the form of a bunch of different images of handwritten digits, along with labels for what they're supposed to be, and it'll adjust those 13,000 weights and biases so as to improve its performance on the training data. Hopefully, this layered structure will mean that what it learns generalizes to images beyond that training data. And the way we test that is that after you train the network, you show it more labeled data that it's never seen before, and you see how accurately it classifies those new images. Fortunately for us, and what makes this such a common example to start with, is that the good people behind the MNIST database have put together a collection of tens of thousands of handwritten digit images, each one labeled with the numbers that they're supposed to be. And as provocative as it is to describe a machine as learning, once you actually see how it works, it feels a lot less like some crazy sci-fi premise, and a lot more like, well, a calculus exercise. I mean, basically it comes down to finding the minimum of a certain function. Remember, conceptually, we're thinking of each neuron as being connected to all of the neurons in the previous layer, and the weights in the weighted sum defining its activation are kind of like the strengths of those connections, and the bias is some indication of whether that neuron tends to be active or inactive. And to start things off, we're just going to initialize all of those weights and biases totally randomly. Needless to say, this network is going to perform pretty horribly on a given training example, since it's just doing something random. For example, you feed in this image of a 3, and the output layer, it just looks like a mess. So what you do is you define a cost function, a way of telling the computer, no, bad computer, that output should have activations which are 0 for most neurons, but 1 for this neuron. What you gave me is utter trash. To say that a little more mathematically, what you do is add up the squares of the differences between each of those trash output activations and the value that you want them to have. And this is what we'll call the cost of a single training example. Notice, this sum is small when the network confidently classifies the image correctly, but it's large when the network seems like it doesn't really know what it's doing. So then what you do is consider the average cost over all of the tens of thousands of training examples at your disposal. This average cost is our measure for how lousy the network is and how bad the computer should feel. And that's a complicated thing. Remember how the network itself was basically a function, one that takes in 784 numbers as inputs, the pixel values, and spits out 10 numbers as its output. And in a sense, it's parameterized by all these weights and biases. Well, the cost function is a layer of complexity on top of that. It takes as its input those 13,000 or so weights and biases, and it spits out a single number describing how bad those weights and biases are, and the way it's defined depends on the network's behavior over all the tens of thousands of pieces of training data. That's a lot to think about. But just telling the computer what a crappy job it's doing isn't very helpful. You want to tell it how to change those weights and biases so that it gets better. To make it easier, rather than struggling to imagine a function with 13,000 inputs, just imagine a simple function that has one number as an input and one number as an output.
That's easy to do.
How do you find an input that minimizes the value of this function? Calculus students will know that you can sometimes figure out that minimum explicitly, but that's not always feasible for really complicated functions. Certainly not in the 13,000 input version of this situation for our crazy complicated neural network cost function. A more flexible tactic is to start at any old input and figure out which direction you should step to make that output lower. Specifically, if you can figure out the slope of the function where you are, then shift to the left if that slope is positive, and shift the input to the right if that slope is negative.
Yeah, that's just what we talked about in the book.
If you do this repeatedly, at each point checking the new slope and taking the appropriate step, you're going to approach some local minimum of the function. And the image you might have in mind here is a ball rolling down a hill.
Yeah.
And notice, even for this really simplified single input function, There are many possible valleys that you might land in,
Yeah.
depending on which random input you start at.
Yeah.
And there's no guarantee that the local minimum you land in is going to be the smallest possible value of the cost function. That's going to carry over to our neural network case as well. And I also want you to notice how if you make your step sizes proportional to the slope, then when the slope is flattening out towards the minimum, your steps get smaller and smaller. And that kind of helps you from overshooting.
So as
Bumping
you
up the complexity
as
a
the
bit.
as the slope starts to even and become flat, you would lower your steps distance, your epsilon x.
Imagine instead a function with 2 inputs and 1 output. You might think of the input space as the xy plane, and the cost function as being graphed as a surface above it. Now instead of asking about the slope of the function, you have to ask which direction should you step in this input space so as to decrease the output of the function most quickly. In other words, what's the downhill direction? And again, it's helpful to think of a ball rolling down that hill. Those of you familiar with multivariable calculus will know that the gradient of a function gives you the direction of steepest ascent. Basically, which direction should you step to increase the function most quickly? Naturally enough, taking the negative...
So think about like you're on top of a hill. So the gradient is the direction of the steepest increase. So think about you're on a hill. You look down in front of you, it's pretty steep. It's like, it's a little bit of a slight steepness to you, but you can walk down it. You look behind you, and it's a flat valley, right? You look to the left of you, and it's a cliff. You look to the right of you, and it's a flat valley, right? So to the right of you, it's a flat valley. Behind you, it's a flat valley. But in front of you, it's a small little down. And then to the left of you, it's a cliff. Well, we would evaluate those directions in all of our, 360 degrees, and we would determine that the cliff is the fastest way down. So that would be the gradient that we would choose. That
gradient
right?
gives you the direction to step that decreases the function most quickly. And even more than that, the length of this gradient vector is actually an indication for just how steep that steepest slope is. Now, if you're unfamiliar with multivariable calculus and you want to learn more, check out some of the work that I did for Khan Academy on the topic. Honestly though, all that matters for you and me right now is that in principle there exists a way to compute this vector. This vector that tells you what the downhill direction is and how steep it is. You'll be okay if that's all you know and you're not rock solid on the details. Because if you can get that, the algorithm for minimizing the function is to compute this gradient direction, then take a small step downhill, and just repeat that over and over. It's the same basic idea for a function that has 13,000 inputs instead of 2 inputs. Imagine organizing all 13,000 weights and biases of our network into a giant column vector. The negative gradient of the cost function is just a vector. It's some direction inside this insanely huge input space that tells you which nudges to all of those numbers is going to cause the most rapid decrease to the cost function. And of course, with our specially designed cost function, changing the weights and biases to decrease it means making the output of the network on each piece of training data look less like a random array of 10 values and more like an actual decision that we want it to make. It's important to remember, this cost function involves an average over all of the training data. So if you minimize it, it means it's a better performance on all of those samples. The algorithm for computing this gradient efficiently, which is effectively the heart of how a neural network learns, is called backpropagation, and it's what I'm going to be talking about next video. There, I really want to take the time to walk through what exactly happens to each weight and each bias for a given piece of training data, trying to give an intuitive feel for what's happening beyond the pile of relevant calculus and formulas. Right here, right now, the main thing I want you to know, independent of implementation details, is that what we mean when we talk about a network learning is that it's just minimizing a cost function. And notice, one consequence of that is that it's important for this cost function to have a nice, smooth output, so that we can find a local minimum by taking little steps downhill. This is why, by the way, artificial neurons have continuously ranging activations, rather than simply being active or inactive in a binary way, the way that biological neurons are. This process of repeatedly nudging an input of a function by some multiple of the negative gradient is called gradient descent. It's a way to converge towards some local minimum of a cost function, basically a valley in this graph. I'm still showing the picture of a function with two inputs, of course, because nudges in a 13,000 dimensional input space are a little hard to wrap your mind around, but there is actually a nice non-spatial way to think about this. Each component of the negative gradient tells us two things. The sign, of course, tells us whether the corresponding component of the input vector should be nudged up or down. But importantly, the relative magnitudes of all these components kind of tells you which changes matter more. You see, in our network, an adjustment to one of the weights might have a much greater impact on the cost function than the adjustment to some other weight. Some of these connections just matter more for our training data. So a way that you can think about this gradient vector of our mind-warpingly massive cost function is that it encodes the relative importance of each weight and bias. That is, which of these changes is going to carry the most bang for your buck. This really is just another way of thinking about direction. To take a simpler example, if you have some function with two variables as an input, and you compute that its gradient at some particular point comes out as 3, 1, then on the one hand, you can interpret that as saying that when you're standing at that input, moving along this direction increases the function most quickly. That when you graph the function above the plane of input points, that vector is what's giving you the straight uphill direction. But another way to read that is to say that changes to this first variable have 3 times the importance as changes to the second variable.
Yeah.
That at least in the neighborhood of the relevant input, nudging the x value carries a lot more bang for your buck. All right, let's zoom out and sum up where we are so far. The network itself is this function with 784 inputs and 10 outputs, defined in terms of all of these weighted sums. The cost function is a layer of complexity on top of that.
Always got something going on out there.
It takes the 13,000 weights and biases as inputs and spits out a single measure of lousiness based on the training examples. And the gradient of the cost function is one more layer of complexity still. It tells us what nudges to all of these weights and biases cause the fastest change to the value of the cost function, which you might interpret as saying which changes to which weights matter the most. So, when you initialize the network with random weights and biases and adjust them many times based on this gradient descent process, how well does it actually perform on images that it's never seen before? Well, the one that I've described here, with the 2 hidden layers of 16 neurons each, chosen mostly for aesthetic reasons, well, it's not bad. It classifies about 96% of the new images that it sees correctly. And honestly, if you look at some of the examples that it messes up on, you kind of feel compelled to cut it a little slack. Now, if you play around with the hidden layer structure and make a couple tweaks, you can get this up to 98%. And that's pretty good. It's not the best. You can certainly get better performance by getting more sophisticated than this plain vanilla network. But given how daunting the initial task is, I just think there's something incredible about any network doing this well on images that it's never seen before, given that we never specifically told it what patterns to look for. Originally, the way that I motivated this structure was by describing a hope that we might have. That the second layer might pick up on little edges, that the third layer would piece together those edges to recognize loops and longer lines, and that those might be pieced together to recognize digits. So, is this what our network is actually doing? Well, for this one at least, not at all. Remember how last video we looked at how the weights of the connections from all of the neurons in the first layer to a given neuron in the second layer can be visualized as a given pixel pattern that second layer neuron is picking up on? Well, when we actually do that for the weights associated with these transitions from the first layer to the next, instead of picking up on isolated little edges here and there, they look, well, almost random, just with some very loose patterns in the middle there. It would seem that in the unfathomably large 13,000 dimensional space of possible weights and biases, our network found itself a happy little local minimum that, despite successfully classifying most images, doesn't exactly pick up on the patterns that we might have hoped for. And to really drive this point home, watch what happens when you input a random image. If the system was smart, you might expect it to either feel uncertain, maybe not really activating any of those 10 output neurons or activating them all evenly. But instead, it confidently gives you some nonsense answer, as if it feels as sure that this random noise is a 5 as it does that an actual image of a 5 is a 5. Phrased differently, even if this network can recognize digits pretty well, it has no idea how to draw them. A lot of this is because it's such a tightly constrained training setup. I mean, put yourself in the network's shoes here. From its point of view, the entire universe consists of nothing but clearly defined, unmoving digits centered in a tiny grid. And its cost function just never gave it any incentive to be anything but utterly confident in its decisions. So with this as the image of what those second layer neurons are really doing, you might wonder why I would introduce this network with the motivation of picking up on edges and patterns. I mean, that's just not at all what it ends up doing. Well, this is not meant to be our end goal, but instead a starting point. Frankly, this is old technology, the kind researched in the 80s and 90s. And you do need to understand it before you can understand more detailed modern variants, and it clearly is capable of solving some interesting problems. But the more you dig into what those hidden layers are really doing, the less intelligent it seems. Shifting the focus for a moment from how networks learn to how you learn, that'll only happen if you engage actively with the material here somehow. One pretty simple thing that I want you to do is just pause right now. To close things off here for the last few minutes, I want to jump back into a snippet of the interview that I had with Leisha Lee. You might remember her from the last video. She did her PhD work in deep learning. And in this little snippet, she talks about 2 recent papers that really dig into how some of the more modern image recognition networks are actually learning. Just to set up where we were in the conversation, the first paper took one of these particularly deep neural networks that's really good at image recognition, and instead of training it on a properly labeled dataset, it shuffled all of the labels around before training. Obviously, the testing accuracy here was going to be no better than random, since everything's just randomly labeled. But it was still able to achieve the same training accuracy as you would on a properly labeled dataset.
Yeah.
Basically, the millions of weights for this particular network were enough for it to just memorize the random data, which kind of raises the question for whether minimizing this cost function actually corresponds to any sort of structure in the image, or is it just, memorization?
Memorize the entire data set of what the correct classification is. And so a couple of, half a year later at ICML this year, there was not exactly rebuttal paper that addressed some aspects of like, hey, actually these networks are doing something a little bit smarter than that. If you look at that accuracy curve, if you were just training on a random data set, that curve sort of went down very slowly in almost kind of a linear fashion. So you're really struggling to find that local minima of possible, the right weights that would get you that accuracy. Whereas if you're actually training on a structured data set, one that has the right labels, you fiddle around a little bit in the beginning, but then you kind of dropped very fast to get to that accuracy level. And so in some sense, it was easier to find that local maxima. And so what was also interesting about that is it brings into light another paper from actually a couple of years ago, which has a lot more simplifications about the network layers, but one of the results was saying how if you look at the optimization landscape, the local minima that these networks tend to learn are actually of equal quality. So in some sense, if you're...
I swear I turned off those alerts. Why is that still playing?
If your data set is structured, you should be able to find that much more easily.
My thanks, as always, to those of you supporting on Patreon.
Wow. Really great video. Really great video. Okay. So that did help kind of solidify what gradient descent is here, right? So we have a gradient, which is just the magnitude and direction for choosing a for the highest direction of loss on your loss function, right? Basically, think about you're on some sort of hill and you're trying to find the quickest way down the hill by examining the magnitude of the steepness downward in all directions, right? Um, so the gradient then, think about like if you're standing on top of a hill, or like think about these things as like three-dimensional structures of hills or mountains, right? You're trying to find these local minimum by choosing and stepping in a direction to where the gradient is maximized for lowering your loss value. You've got the right terrain picture. The hill picture. Think of a horizontal position as all your model weights. And the height is your loss value. So the loss function is just a giant landscape. Hills equals high loss, bad model. Values equal low loss, good model. What the gradient actually tells you. The gradient points in the direction of the steepest increase in loss, right? So we're standing on the hill. We see, okay, that way is a cliff down. That way is my steepest, right? The gradient points in the direction of the steepest increase in loss. So a gradient in the uphill direction, negative gradient is downhill direction. You said stepping in a direction to where the gradient is maximized for lowering your loss. Correct? You step in the direction of the negative gradient. You step in the direction of the negative gradient to lower your loss. So the weight of our new becomes the weight of our old minus the, whatever these calculus symbols mean, pertaining to the gradient value, right? The weight, the loss function applied to the gradient, something of the weight. At your current position on the hill, the gradient tells you go this way to go up the fastest, but you want to go down. So you do exactly the opposite of that direction. The gradient is maximized for lowering loss. The two mixes the two ideas together. The gradient is the compass pointing uphill. Negative gradient is compass flipped pointing downhill. So you move along the high dimensional landscape using local slope information because you don't want to overshoot. So like you said at the end there, you're using controlled movements to step along the gradient down to the most optimized path to reach the local minimum fastest by choosing or following the gradient, which points you in or following the negative gradient or the inverse positive gradient for that specific weight vector or whatever. Now we have the ability as the localized slope begins to taper, we know that we could be transitioning into the bottom of the local minimum. So we want to maybe slow down our steps, which maybe be like our bias. Yes, your mental model is right. You follow the negative gradient, right? As your slope begins to taper, we are transitioning into the local minimum. Near minimum, the slope gets smaller, gradient shrinks to 0. Updates become less dramatic. Should we slow down near the minimum? Yes. Huh. Okay. closer way to the end here. Not really. We might be able to make it by the end though. Let's try it. Let's see. Okay, stochastic gradient descent. Given a differentiable function, it's theoretically possible to find its minimum analytically. It's known that a function's minimum is a point where its derivative is 0. Right, a flat slope. So all you have to do is find all the points where the derivative goes to 0 and check for which of these points the function has the lowest value. Right, you find all the local minimums and check for the lowest y value. Right. Applied to the neural network, that means finding analytically the combination of weight values that yield the smallest possible loss function. This can be done by solving the equation, right, for gradient of f of the weights for some weight equals to 0 for a weight, w. So we're trying to find where the gradient is equal to 0 given some function of weights and some weight. This is a polynomial equation of n variables, where n is the number of coefficients in the model. Although it would be possible to solve such an equation for n equals 2 or n equals 3, doing so is intractable for real neural networks, where the number of parameters is never less than a few 100,000 and can sometimes be in the billions. Instead, you can use up to the 4-step algorithm outlined at the beginning of this section. Modify the parameters little by little based on the current loss value on a random batch of data. Because you're dealing with a differentiable function, you can compute its gradient, which gives you an efficient way to implement step 4. If you update the weights in the opposite direction from the gradient, the loss will be a little less every time. So 1 is draw a batch of training samples x, corresponding targets, y underscore true. You run the model on x, the training samples, to obtain predictions, y predictions. This is called the forward pass, right? We compute a loss on the model between the predictions and our true. We compute a gradient of the loss. So we compute, okay, does this loss have, magnitude, a negative gradient downwards? As we take steps and adjust these batches, does our gradient, or whatever, I'm not sure exactly. This is called the backward pass. Move the parameters a little in the opposite direction from the gradient. For example, the weight minus equals 2, lowering the weight by a factor of the learning rate times the gradient, thus reducing the loss on the batch a bit. The learning rate here, would be a scalar factor modulating the, quote, speed of the gradient descent process. Easy enough. What we just described is called mini-batch stochastic gradient descent, mini-batch SGD. The term stochastic refers to the fact that
You're not that guy, pal. Trust me. You're not that
That's
guy.
so weird. Why is that still going?
Okay? Absolutely.
I don't get it. Oh, I think I had these alerts in these other scenes. I tried to remove those alerts. Alright, we'll let it be there. Hey, what's up, Chad? The term stochastic refers to the fact that each batch of data is drawn at random. Stochastic is a scientific term, synonym of random. Figure 218 illustrates what happens in one dimension when the model has only one parameter and you have only one training sample. Right? We have a loss value in the y and a parameter value in the x. We have some learning rate, which is basically the steps that we're going to take, the movement along the gradient. You can see intuitively that it's important to pick a reasonable value for the learning rate factor. If it's too small, the descent down the curve will take many iterations, and it could get stuck in a local minimum. If learning rate is too large, your updates may end up taking you completely random locations on the curve. Note that a variant of the mini batch SGD algorithm would be drawn a single sample and target at each iteration, rather than drawing a batch of data. This would be true. Note that a variant of the mini batch SGD algorithm would be to draw a single sample and target at each iteration, rather than drawing a batch of data. This would be true SGD as opposed to mini batch SGD. Alternatively, going to the opposite extreme, you could run every step on all data available, which is batch gradient descent. Each update would then be more accurate but far more expensive. The efficient compromise between these two extremes is to use mini batches of reasonable sizes. Right? If you're going to compute the whole thing, it's very computationally intensive. But if you were to draw a single sample at each target iteration, that would be true SGD. So you kind of do a little mix of the both. Although figure 218 illustrates gradient descent in a 1D parameter space, in practice, you'll use gradient descent in highly dimensional spaces. Every weight coefficient in a neural network is a free dimension in the space, and there may be tens of thousands or even millions of them. To help you build intuition about loss surfaces, you can also visualize gradient descent along a 2D surface, as shown in figure 219. But you can't possibly visualize what the actual process of training a neural network will look like. You can't represent a million dimension space in a way that makes sense to humans. As such, it's good to keep in mind that the intuitions you develop through these low dimensional representations may not always be accurate in practice. This has historically been a source of issues in the world of deep learning research. Right? Where we have a 2D loss surface here with this gradient, and you can see our gradient is our loss value as it gradients to a lower value. We start out at a pretty high loss value with given those random inputs or random first weight values. We adjust and we slowly trickle our way to the local minimum down the gradient. We follow the gradient, right? And remember, the gradient in multivariable calculus is the magnitude and direction for where the loss function is maximized for the loss if you follow it. Additionally, there exist multiple variants of SGD that differ stochastic gradient. Additionally, there exist multiple variants of stochastic gradient descent that differ by taking into account previous weight updates when computing the next weight update, rather than just looking at the current value of the gradients. There is, for instance, stochastic gradient descent with momentum as well as autograd RMS prop, and several others. Such variants are known as optimization methods or optimizers. In particular, the concept of momentum, which is used in many of these variants, deserves your attention. Momentum addresses two issues with stochastic gradient descent: convergence speed and local minima. Consider figure 220, which shows the curve of a loss function of a model parameter. Consider figure 220, which shows the curve of a loss as a function of a model parameter. Right, we have some loss value in our y and parameter value in our x. We have some local minimum and a global minimum here. As you can see, around a certain parameter, there is a local minimum. Around that point, moving left would result in an increase in loss, but so would moving right. You're kind of stuck in the bottom of this hill, of this valley, I mean. If the parameter under consideration were being optimized via stochastic gradient descent with a small learning rate, then the optimization process would get stuck at the local minimum instead of making its way to the global minimum. You can avoid such issues by using momentum, which draws inspiration from physics. A useful mental image here is to think of optimization projects as a small ball rolling down the loss curve. If it has enough momentum, the ball won't get stuck in a ravine and will end up in the global minimum. Momentum is implied by Momentum is implemented by moving the ball at each step based not only on the current slope value, current acceleration, but also on the current velocity, resulting from past acceleration. In practice, this means updating the parameter w based not only on the current gradient value, but also on the previous parameter update as well, such as in this naive implementation, right? We have a past velocity and a momentum. While loss is greater than 0.01, we get parameters, which is weight, loss, and gradient. We say the velocity is equal to past velocity times momentum minus linear rate times gradient. And then we save the weight is now updated accordingly with the velocity update. And then we say past velocity is now equal to velocity, and we update the parameter. Chaining derivatives, the back propagation. Chaining derivatives, the back propagation algorithm. In the previous discussed algorithm, we casually assumed that because a function is differentiable, we can easily compute its gradient. But is that true? How can we compute the gradient of a complex expression in practice? In our two-layer network example, how can we get the gradient of the loss with regards to the weights? That's where the backpropagation algorithm comes in. The chain rule. Backpropagation is a way to use the derivative of simple operations such as addition, ReLU, or tensor product to easily compute the gradient of arbitrary complex combinations of these atomic operations. Crucially, a neural network consists of many tensor operations chained together, each of which has a simple known derivative. For instance, the model from our first example can be expressed as a function parameterized by the variables w1, b1, w2, and b2, belonging to the first and second dense layers, respectively, involving the atomic operations matmul, ReLU, softmax, and addition, as well as our loss function, loss, which are all easily differentiable. Loss value equals to our loss function with the input of the true values for y, and we call matmul of our inputs for w1 plus a bias 1. We apply a ReLU on that for weight 2, and we matmul the resulting value of that with weight 2. We add bias 2 and compute softmax. Calculus tells us that such a chain rule of functions can be derived using the following identity called the chain rule. Consider two functions f and g, as well as the composed function fg, such that y equals to fg of x, which is equal to f of g of x. Def fg of x, x1 is equal to g of x, y is equal to f of x1, return y. Then the chain rule states that the gradient yx is equal to the gradient yx1 times gradient x1x. This enables you to compute the derivative of fg as long as you know the derivatives of f and g. The chain rule is named like this because when you add more intermediate functions, it starts to look like a chain. So you just compute the gradient of all of its intersections. Applying the chain rule to the computation of gradient values of a neural network gives rise to an algorithm called backpropagation. Let's see how this works concretely. So now when shifting to backpropagation and relating that to gradients and the chain rule, we know that by chaining together functions such as f of g of x, which is just equal to fg of x, right? We could then compute the gradient at each inner node or whatever. How does this work? the idea is the key idea. A neural network is a chain of functions. You wrote f of g of x is exactly the right structure on a neural network. More general, plain text, x calls g, calls h, calls f, calls loss. So the loss is equal to f of h of g of x, right? Each layer is just a function. Forward pass versus back pass. Forward pass is the computed value. You compute step by step. So a is equal to g of x, b is equal to h of a, L is equal to f of b. You store intermediate values. Back pass, compute gradients. Now we ask, how does chaining x or weights inside g, h slash f affect the loss? Here's where the chain rule comes in. So we have the loss is equal to f of g of x. The derivative of this is the derivative of the loss over the derivative of the gradient times the derivative of the gradient over the derivative of x. Meaning total sensitivity equals product of local sensitivities. Intuition. Each function contributes to a local scope, how x affects intermediate output, how intermediate output affects loss. So effect on x on loss equals the multiplier of all local effects along the path. Concrete picture. Think of a pipeline. Now reverse the direction. Start from loss. dl over dl equals 1. dl over db equals dl over dl times df over db. Each node only needs its local derivative and the gradient coming from above, and then multiplies it and passes it backwards. So every node answers. If I change my input slightly, how does my output change? Interesting. Applying the chain rule to the computation of the gradient values of a neural network gives rise to an algorithm called backpropagation. Let's see how that works concretely. Automatic differentiation with computation graphs. A useful way to think about backpropagation is in terms of computation graphs. A computation graph is the data structure at the heart of deep learning revolution. It's a directed acyclical graph of operations. In our case, tensor operations. For instance, figure 221 is the graph representation of our first model, where we have input, we compute the dot product of our weight 1 and add our bias, we compute some ReLU, we go on to our second layer, our dense layer, we compute the dot product of that result with our weight bias 2, and then add our bias, and we compute a softmax. We compare our true values with the resulting of that, which is our y predictions, right? We compute that a loss function, we get a loss value. We now need to backpropagate, right? Computation graphs have been extremely successful abstraction in computer science because they enable us to treat computation as data, a computable expression encoded as a machine-readable data structure that can be used as the input or output Computation graphs have been an extremely successful abstraction in computer science because they enable us to treat computation as data, a computable expression is encoded as a machine-readable data structure that can be used as the input or output of another program. For instance, you could imagine a program that receives a computation graph and returns a new computation graph that implements a large-scale distributed version of the same computation. This would mean that you could distribute any computation without having to write the distribution logic yourself. Or imagine a program that receives a computation graph and can automatically generate the derivative of the expression it represents. It's much easier to do these things if your computation is expressed as an explicit graph data structure rather than, say, lines of ASCII characters in a .py file. To explain back propagation clearly, let's look at a really basic example of a computation graph. We'll consider a simplified version of the graph in figure 221, where we only have one linear layer, and where all variables are scalar. Shown in figure 222, we will take the two scalar variables w and b, a scalar input x, and apply some operations to them to combine into an output y. Finally, we'll apply an absolute value error loss function. Loss equals to the absolute value of the y true minus the y, since we want to update the weight and bias in a way that would minimize the loss value. We are interested in computing the gradient for the loss value of this bias and the gradient for this loss value of this weight. So we have some input x, right? We are going to compute the dot product against our weights. That's going to give us some x1. We're going to add our bias. That's going to give us some x2, which is the result of some loss value, right? We have our x2. We then feed that x2 into a loss function with our y trues, our expected y values, and compute how far off was our x2, right? This is our y prediction, basically. Let's set concrete values for the input nodes in the graph. That is the input x, the target y true, and the weight and bias. We propagate these values to all nodes in the graph from top to bottom until we reach loss value. This is the forward pass, right? So we have our input is 2. We compute some weight to get 6. We add on a bias of 1 to get 7. We have our expected value is 4. We have a loss value of 3. Now let's reverse the graph. For each edge in the graph going from A to B, we'll create an opposite edge from B to A and ask, how much does B vary when A varies? That is, what is the gradient of B, A? We'll annotate each inverted edge with this value, figure 224. This backward graph represents the backward pass, right? So we have some loss value, which is fed into our loss function with our true values of 4, right? We compute a gradient for the loss value and the x2 that was given out, which is equal to 1. We then add a bias and compute a gradient of x2, the result of this here. And then we have a gradient computation for x2 here and x1, and then back to the original x1 and the weight. We have the gradient loss value comma x2 is equal to 1 because x2 varies by an amount epsilon. Loss value equals to the absolute value of 4 minus x2 varies by the same amount. Yeah, so x2 varies by some epsilon amount. Gradient x2, x1 equals 1 because x1 varies by amount epsilon. x2 equals to x1 plus b, which equals to x1 plus 1, varies by the same amount. And gradient x1 comma weight equals to 2 because as weight varies by an amount epsilon, x1 equals to x times weight, which equals to 2 times weight, varies by 2 times epsilon. What the chain rule says about this backward graph is that you can obtain the derivative of a node with respect to another node by multiplying the derivatives for each edge along the path linking the two nodes. For instance, gradient loss value comma w equals gradient loss value comma x2 times gradient x2 comma x1 times gradient x1 comma w. By applying the chain rule to our graph, we obtain what we're looking for. If there are multiple paths linking the two nodes of interest A and B in the backward graph, we would obtain gradient BA by summoning contributions of all the paths. And with that, you just saw backpropagation in action. Backpropagation is simply the application of the chain rule to a computation graph. There's nothing more to it. Backpropagation starts with the final loss value and works backward from the top layers to the bottom layers, computing the contribution that each parameter had in the loss value. That's where the name backpropagation comes from. We backpropagate the loss contributions of different nodes in a computation graph. Nowadays, people implement neural networks in a modern framework that are capable of automatic differentiation, such as JAX, TensorFlow, and PyTorch. Automatic differentiation is implemented with kind of computation graph previously presented. Automatic differentiation makes it possible to retrieve the gradients of arbitrary compositions of differentiable tensor operations without having to do any extra work besides writing down the forward pass. When I wrote my first neural network in C in the 2000s, I had to write my gradients by hand. Now, thanks to modern automatic differentiation tools, you'll never have to implement backpropagation yourself. Consider yourself lucky. I'm going to take this. The author is really glazing over this stuff way too fast. I'm sure this is where a lot of people get lost. This section is describing backpropagation correctly, and if it helps you mentally strip away the wording and see the mechanics, I'll translate into a clean mental model. What the computation graph really is, you have a chain like this. The weight goes to x1, which goes to x2, which goes to y, which computes a loss. But more concretely, x equals to input, the weight and bias is some parameter, x1 is the dot product of x, the input times the weight, x2 is the translation of x1 plus the bias, and y is equal to x2. Loss is equal to the absolute value of y true minus the y value, or x2. So it's just a sequence of simple operations. Each arrow is just a function. Forward pass evaluates values. You normally do math left to right. Compute x1, compute x2, compute y, compute loss. Nothing special yet. You just store intermediate results. In the backward pass, you compute sensitivity. Now we reverse the direction, but not literally reversing computation. We are asking, if I change this node slightly, how does that change the final loss? That's a derivative question. The key rule, or chain rule. If A goes to B, which goes to C, which computes a loss, then in plain text, the derivative of loss over derivative of A equals to the derivative of loss over the derivative of C times the derivative of C over the derivative of B times the derivative of B over the derivative of A. So multiple local sensitivities along the path. What each edge derivative means. Let's interpret your example. x2 plus x1 plus b. So sigmoid x2 over sigmoid x1 equals to 1. What is this? What is this? Meaning changing either x1 or b changes x2 to 1 to 1. x1 equals the dot product of x times weights. So this becomes x equals to derivative of x1 over weight. So if x is equal to 2 here, meaning changing w changes x1 scaled by, changing w x1 scaled by input x. We'll definitely probably have to watch that, the next video by 3 Blue 1 Brown. Let's just finish up this chapter though, so I can get it uploaded. Come on, stop over scrolling. Looking back at our first example, you're nearing the end of this chapter, and you should now have a general understanding of what's going on behind the scenes in a neural network. What was a magical black box at the start of the chapter has turned into a clearer picture as illustrated in figure 226. The model composed of layers that are chained together maps the input data to predictions. The loss function then compares these predictions to the targets, producing a loss value, a measure of how well the model's predictions match what we expected. The optimizer uses this loss value to update the model's weights. Let's go back to the first example and review each piece of it and highlight what you've learned in the previous sections. This was the input data, where from the MNIST dataset we load data for training images and labels and test images and labels. We reshape, and then we change the type of each of those training and testing images. Now you understand that the images are stored in NumPy tensors, which are here formatted as 32 float tensors of shape 60,000 by 784 training data and 10,000 by 784 for testing data respectively. This was our model, right? Now you understand that this model consists of a chain of 2 dense layers, that each layer applies a few simple tensor operations to the input data, and these operations involve weight tensors. Weight tensors, which are attributes of the layer, are where the knowledge of the model persists. This was the model compilation step. Now that you understand that sparse categorical cross entropy is the loss function that's used as a feedback signal for learning the weight tensors, which is the training phase, which the training phase will attempt to minimize. You also know that this reduction of loss happens via mini-batch stochastic gradient descent. The exact rules governing a specific use of gradient descent are defined by the atom optimizer passed as the first argument. Finally, this was the training loop. Model.fit, given the training images and the training labels, epochs is 5, and batch size is 128. Now you understand what happens when you call fit. The model will start to iterate on the training data in mini batches of 128 samples 5 times over. Each iteration over all the training data is called an epoch. For each batch, the model will compute the gradient of the loss with regard to the weights, using the back propagation algorithm, which derives from the chain rule in calculus, and moves the weights in the direction that will reduce the value of the loss for this batch. After these 5 epochs, the model will have performed 2,345 gradient updates, 469 per epoch, and the loss of the model will be sufficiently low that the model will be capable of classifying handwritten digits with high accuracy. At this point, you already know most of what there is to know about neural networks. Let's prove it by re-implementing a simplified version of the first example step by step, using only low-level operations. Re-implementing our first example from scratch. What's better to demonstrate full, unambiguous understanding than to implement everything from scratch? Of course, what, quote, from scratch means here is relative. We won't implement basic tensor operations, and we won't implement backpropagation, but we'll go such a low level that each computation step will be made explicit. Don't worry if you don't understand every little detail in this example yet. The next chapter will dive into more detail into the Keras API. For now, try to follow the gist of what's going on. The intent of this example is to try to help crystallize your understanding of the mathematics of deep learning using a concrete implementation. Let's go. A simple dense class. You've learned earlier that the dense layer implements the following input transformations, where the weights and biases are model parameters, and activation is the element vice function, usually a ReLU function. We have an output is equal to activation, which takes in a map multiplication of our input plus W. So we map multiply our input in W, and then we apply a addition of our bias and use our activation on that. Let's implement a simple Python class called naive dense that creates two Keras available weights and biases and exposes a dunder call method that applies the previous transformation. So we import Keras and we import from Keras ops. We have a naive dense, right, which is going to be kind of a mock layer that we're going to implement with Python here. In our initializer, we have input size, output size, and activation is none. We set self.activation equal to activation, and we say that the self.big W, or weights, is equal to Keras.variable. This creates a matrix of weight, shape, input size, output size, initialized with random values drawn from a uniform distribution. Got you. So we apply a shape parameter equal to input output size and initializer equals to uniform. So this just creates a matrix weight of shape, input output size. Then we create a bias, self.b, which is Keras.variable, shape equals to the output size, so it's a 1D tensor, and we initialize it to all zeros. All right, we have a call under special method, which applies the forward pass. So when we call this, given the inputs, we apply operation mapmul inputs and self.weights. We add the bias. We do the activation, and then we return the resulting value. And we have a property, the convenience method for retrieving the layer's weights, just a property of weights, which returns a list of self.w, self.b. That makes sense. I'm following all that. A simple sequential class. Now let's create a naive sequential class to chain these layers. It wraps a list of layers and exposes a dunder call method that simply calls the underlying layers on the inputs in order. It also features a weights property to easily keep track of the layers' parameters. So naive sequential is going to chain our layers together. So we have layers, which is going to be applied to self.layers, probably in the form of like a list of layers. And when we call this, we have x equals to inputs. For every layer, we call our layer x equals to x. And then we return the value given back. We have a property of weights, which is just a list of weights. For layer in self.layers, we add to the list of weights the layer.weights. Just appending a list of lists, right? Using this naive dense class and naive sequential class, we can create a mock Keras model. So model equals to naive sequential, where we put in those two layers of naive dense. And then we assert that the model weights is equal to 4. Model weights. Weights equals layer.weights. So this has, oh, layer.weights is this. It's the property, right? Got you. So you assert that the model has 4 weights. Right, which would be a weight and a bias for each layer. And we have 2 layers, so that makes sense. 4 weights, 2 weights per layer. Got you. A batch generator. Next, we need a way to iterate over the MNIST data in mini batches. This is easy. We just create a class and import math using and create a class batch generator. Our initializer has images, labels, and batch size. We assert that the length of images and length of labels is equal. Right, we say the index is 0, self-image is image, self-labels is labels, self-batch size is batch size, and the number of batches equals to math.ceiling of length of images over batch size. So it just gives us the maximum number of batches we're going to make. We're probably going to loop over batches, right, and create batches. Or we're probably going to loop over the num batches and create batches, right? if we call next images equals to self.index through self.index plus batch size. So it's just getting us the next batch of images and labels using kind of like a pagination technique through the list slicing. Running one training step. The most difficult part of the process is the training step, updating the weights of the model after running it on one batch of data. We need to compute the predictions of the model for the images in the batch, compute the loss value for these predictions given the actual labels, compute the gradient of the loss with regard to the model's weights, and move the weights by a small amount in the direction opposite to the gradient. So one training step, given a model, images batch, and labels batch, we run the forward pass. We call model images batch, which returns back our predictions. Model. Models are naive sequential model, right? So we give in our model. In the batch of images, you compute a loss. You have an average loss across all operations. Compute the gradient for loss with regard to the weights. We haven't defined this function yet. And then we return a loss after updating all the weights. The weight update step. As you already know, the purpose of the weight update step, represented by the update weights function, is to move the weights by a, quote, bit in a direction that will reduce the loss on this batch. The magnitude of this move is determined by the learning rate, typically a small quantity. The simplest way to implement this update weights function is to subtract gradient times the learning rate from each weight. So we have some very small learning rate value here, 1 times 10 to the negative 3. Right, after update weights given some gradients and some weights, right, for every gradient and weight in a zip of gradients and weights together, right, which will unpack each gradient and weight, looping over them one by one into these values. Assign a new value to the variable in place. In practice, you will almost never implement a weight update step like this by hand. Instead, you would use an optimizer instance from Keras like this. So optimizers dot stochastic gradient descent with a learning rate of 1e to the negative 3 is our optimizer, and you would apply gradients on the actual zip of gradients and weights together. Gradient computation. Now there's just one more thing we're still missing. Gradient computation, represented by the get gradients of loss WRT underscore weights function in listing 2.9. In the previous section, we outlined how we could use the chain rule to obtain the gradients of a chain of functions given their individual derivatives, a process known as backpropagation. We could re-implement backpropagation from scratch here, but that would be rather a cumbersome, especially since we're using a softmax operation and cross entropy loss, which have fairly verbose derivatives. Instead, we can rely on the automatic differentiation mechanism that's built into one of the 4 low-level frameworks supported by Keras, such as TensorFlow, JAX, or PyTorch. For the sake of this example, let's go with TensorFlow here. You'll learn more about TensorFlow, JAX, and PyTorch in the next chapter. The API through which you can use TensorFlow automatic differentiating capabilities is the tf.gradientTape object. It's a Python scope that will record the tensor's operations that run inside it in the form of a computation graph, sometimes called a tape. This graph can be used to retrieve the gradient of any scalar values with respect to any set of input values. So import TensorFlow as tf. tf.zero's shape is blank. Initiates a scalar tensor with value 0. Opens a gradient tape scope with TensorFlow.gradientTape as tape. So we're going to use a context manager here. Inside the scope, apply some tensor operations to our variable 2 times x plus 3. Uses the tape to retrieve the gradient of the output y with respect to our variable x. Tape.gradientYx. the gradient of y with respect to x. Let's rewrite our function one training step using the TensorFlow gradient tape, skipping the need for separate get gradient of loss with respect to weights function. So one training step, given the model and batches of images and labels for this batch, we're going to use the gradient tape and pass our images batch into our model, which returns us predictions. We compute a loss using our loss function, sparse categorical cross entropy. We compute an average loss across all of those loss values. Our gradients equals to tape.gradient, average loss, and our model weights. We update our weights and return the average loss. Now that our per batch training step is ready, we can move on to implement an entire epoch of training. Here's the full training loop. An epoch of training simply consists of repeating the training step for each batch in the training data. And the full training loop is simply the repetition of one epoch, right? So you're just going to do this for every batch, for every epoch, right? For a counter and range of epochs, and for batch, you generate batches, and for every batch counter, right, in range of batch generator. So you just do that one training step, right, for every batch, for every epoch. Kind of like what we do in our MIT 60002, kind of our computational modeling and stuff. So to test drive it is this. Evaluating the model. We can evaluate the model by taking the argmax of its predictions over the test images and comparing it to the expected labels. So predictions equals models test images, predicted labels equals ops argmax, predictions axis equals 1. Matches equals to prediction labels equals to matches is equal to the predictions labels that are equal to test labels, and the mean of matches. All done. As you can see, it's quite a bit of work to do by hand, what you can do in a few lines of Keras code, but because you've already gone through the steps, you should now have a crystal clear understanding of what goes on inside a neural network when you call fit. Having this low-level mental model of what your code is doing behind the scenes will make you better able to take advantage of high-level features of the Keras API. Dang, what a chapter. Holy crap. What a chapter. Wow. Wow, wow, wow. That was a lot of info. Right. We're going to need to honestly take some time, I think, to really absorb this chapter before really moving on to chapter 3. Because this starts to introduce, TensorFlow, PyTorch, Jackson, Keras. So we start to kind of abstract using these libraries over the top of our learning that we did in chapter 2. All right. I also need to go back through and take some notes, but I'm not doing that today. I'm done for today. We've been going for 3 hours and 30 minutes almost. Let me go ahead and sign off on the YouTube for the recording. All right, guys, thanks so much for watching. Let's sign off for that one. Let's go up to the top here. All right, that was chapter 2, the mathematical building blocks of neural networks. That was really, really dense with a lot of new concepts. So please take your time going through that. I myself will be going back through this, watching videos, and solidifying the information because it was a lot. The notes that you see can be found in my GitHub repo, link down below. I need to go back through and polish up these notes for some of the more dense material. And this is the chopped up version of the entire live stream, which was over 3 to 5 hours long, going through this entire chapter. If you guys would like to join me daily, gosh, I suck. If you guys would like to join me daily around 7 p.m. PST as I teach myself computer science and programming from the ground up through books like this and building projects. All right, guys, this was chapter 2 of Deep Learning with Python. I'll see you guys in the next one. All right, cool. I'll stop the recording there. Let's get caught up on some chats here. Sheesh. That was a lot. Get caught up on some chats. What's up, Mon? Yeah, our channel, we got like 1,000 subs in like 2 or 3 days. It's really quite crazy. Our first video of reading this book really popped off. But I bet you, I guarantee you, chapter 2 will not have as much watches because I guarantee you people are going to fall off when it starts getting dense. Like, they're going to drop off like flies. I think as soon as you know Calc 3, 4, their intermediate results from Calc. We can talk more about the math more. This is called del, like delta, but it's used for partial derivatives. It says the del, oh, the little d that's used in that little thing. Okay, it's for delta with respect to weights, meaning that you're taking the derivative of the function of the variable is the weight. Dot product x of w is basic. Derivative rule says that x equals to a times w. Rolling a ball into a hole on a 1 million dimension surface. Why are the weights 4? I think, let's go back here. The weights were 4 because it was 2 per layer in terms of, if you go back and look at the weights here, it returns the length of 2, right? So the length of the model dot weights altogether is 4, as there'll be self weight 1, self bias 1, self weight 2, self bias 2. All right, you guys, that was a long chapter. I think what I'm gonna do tomorrow is I'm gonna do a breakdown video of like chapter 1. Ooh, looks like my screen glitched. Hold up. My screen glitched. Hold on. Let me restart that. Come on. Come on. Let's go. There we go. I'm gonna go back through and do a recap of chapter 1, like of my notes, and like kind of do like a summary video. And I'm also gonna do that for chapter 2. I think it'll really help to solidify the information and whatnot. Sorry, I'll show you again, Mahan, here. Look, so the weights applied to the naive dense layer is a list of self.w, self.bias, right? The self.weight and self.bias. So if we call weights here, you just append to a list of weights and return weights. And so we're calling length of model dot weights, which is 4, which is 2 w's and 2 biases. Oh, it's still not showing. What the heck? Come on. There you go. Right here. So the layer, right, this is the dense layer reimplementation here, has a property of self.w comma self.b, right? And these are just 2 integers, the number of weights and the number of biases for this layer. And so we're just going to, in the sequential for the actual model itself, we're going to just append all the weights together, the list, into one giant list. So you get a length of 4 for each, 2 for each layer. All right, you guys. This was a long one. I don't know. I don't know. Like you guys, like I'm gonna keep going for sure, but it's looking a little rough, right? We started off hot, and then it's kind of like the typical thing, the trend of learning. You kind of start off hot, and then as you get into some really thick material, you kind of regress a little bit, and then that regression can feel pretty negative. Like it can feel pretty bad, and like I want to quit, or whatever. But once you kind of are able to dig yourself out of that regression, the learning can kind of really take off. So we've got to keep sticking at it, keep thinking about it. This is our first ever introduction to stochastic gradient descent, to gradients, multivariable calculus, all that jazz. So it's going to be pretty difficult to wrap our head around right off the jump, but I think with some time we should be able to understand the gist of it. So thanks so much for being here tonight, y'all. I'll see you guys later. We're almost at 6,500 subscribers. It's pretty crazy. We no worries, Mahan. Thanks for being here, my boy. We're almost to 6,500 subs. I gained like almost 1,000 subscribers in like 3 days or something like that. 4 days. It's pretty crazy. It seems like the machine learning, the first video has been really popping off. It's almost to like 10,000 views on YouTube, which is kind of funny because I was just actually thinking to myself, I was like, man, I've been doing this YouTube thing for 2 years and I have yet to have a video ever like go viral, or like, all of my videos have less than like 500 views. My streams are all pretty dead for the most part. So it's like, it's crazy. I was like, it's like the YouTube algorithm really has been fighting us this whole time. And then finally, like it was kind of crazy on that. Yeah, 8.1 thousand views on that one from 3 days ago. But it's going to be interesting, as I think that the chapter 2, we're going to lose a lot of people because this is just way more dense. Hey, Nasir. Probably to get fluent about 6 months, but I learned it in about like 2 or 3. All right, you guys, thanks so much for being here. I'll see you guys next time. Tomorrow, I'll do a long stream tomorrow where we'll continue on. We'll probably work on some C practice problems in our C book, maybe our project, and continue on with